Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 32nd video lecture. And today we want to talk about two main things. One, it has to do with the continuity and the relationship it has with connectedness, and then another has to do with left and right-handed limits of functions. So let's go ahead and get started with the theorem. The theorem says if f is a continuous mapping of a metric space X into a metric space Y, and if E is a connected subset of X, then f of E is a connected subset of Y. Okay, the proof is going to be by contradiction, so let's start off proof. Here I'm going to write down the hypothesis. We'll assume that F is continuous. Let's say is a continuous mapping of a metric space X into a metric space Y and let E be a connected subset of X. Suppose f of E is not connected. Okay. So f of E is in Y. Suppose it's not connected. Then, what does it mean for not to be connected? F of E would be equal to A union B, where A and B are non-empty separated subsets of Y. Now, what we're going to look at is two sets. We're going to find G to be equal to E intersect the inverse image of A under F, and we're going to find another subset H to be equal to E intersected with the inverse image of B under F. And now we're going to make a claim about what E is. Okay, so as a claim, this is an easy claim to prove. Its E is equal to G union H. All right, let's do a proof of claim. Okay. So we're going to show that they're subsets of each other, these two sets. So let x sub 1 be an element of E. That says, that will imply that f of x sub 1 is an element of f of E. So we're assuming that f of E is equal to A union B. So that means that f of x sub 1 is an element of A union B. So we have two cases. Case 1, f of x sub 1 is an element of A. Then that means x sub 1 is an element of the inverse image of A under F. And so that means that x sub 1 is an element, since it's an element of E and an element of the inverse image of A under F, that x sub 1 is an element of the intersect these two sets. And so that constitutes what G is. So x sub 1 is an element of G, thus x sub 1 is an element of G union H. Case 2, that's if f of x sub 1 is in B. So x sub 1 is an element of the inverse image of B. This is very similar. So since x sub 1 is in E and x sub 1 is in the inverse image of B, that says x sub 1 is an element of E intersect the inverse image of B, and that's what H was defined to be. And so that means that x sub 1 is not only in H, but x sub 1 is in G union H. So we've just shown that in all cases that E is a subset of G union H. That's half of what we wanted to show. Now, let's let x sub 2 be an element of G union H. And what we want to show is that x sub 1 is in E. So, we have two cases again. Case 1 is x sub 2 is an element of G. Then, by the definition of G, x sub 2 is going to be an element of, let's see, E
intersect the inverse image of A. So x of 2 is in E. Okay. Case 2, x of 2 is an element of H. Then that says that x of 2 is an element, what H is defined to be, is E intersects the inverse image of the preimage B. And so that says that x of 2 is in E. If it's in the intersection, it's got to be in E in both sets. So in all possible cases, x of 2 is an element of B. So that said that G union H is a subset of E. So that proves the plane. I'll just write this conclusionary statement. So that means that E is equal to G union H. That ends to prove the plane. Okay, now next thing we want to observe is that since A is contained in its closure, remember what its closure is. That's A union its limit point, so A is a subset of it, of A closure. Then what we have is G is a subset of F inverse of A remember what G was defined to be. G was defined to be F inverse of A, the inverse image of A under F, intersecting with E. And so G is a subset of this, and which is a subset of the inverse image of A closure. A closure. Now, since F is continuous, we had a fact that said, hey, inverse images of open sets were open, but also inverse images of closed sets would be open. And we know A closure is closed. Then the inverse image of A closure is closed in X. And, okay, let me practice that. So since G is contained in this closed set, then G closure is also contained in this closed set. Okay. So what this says is that F of G closure will be contained in A closure. Now here's my second claim. Is that F of H, that's going to be equal to B. So here's the proof of the claim. So let's let y sub 1 be an element of f of h. Okay. Then there exists an x sub 1 element of h Oops, let me back up. Let us replace h by what it's equal to. So y sub 1 is an element of f of equals E intersect the inverse image of B. That's where one is, y sub 1 is. So what does that say? So there exists an x sub 1, an element of E intersect the inverse image of B, such that f of x sub 1 is equal to y sub 1. Okay? So x sub 1 is an element of E, and x sub 1 is an element of the inverse image of B under F. So f of x sub 1 is an element of B. And so that says y sub 1 is an element of B. And that's what we were trying to show partly. So that says that f of h is contained in B. Okay. Now, in the reverse direction, let's let y sub 2 be an element of B. Since f of E is equal to A union B, then y sub 2 is an element of f of E. So, there exists an x sub 2 element of B such that f of x sub 2 is an element of x sub 2, f of x sub 2 is equal to y sub 2, I should say. Since y sub 2 is an element of B, and f of x sub 2 is equal to y sub 2, then x sub 2 is an element of the inverse image of B. So, that means that x sub 2 is an element of E and the inverse image of B, so it's in their intersection. So, f of x sub 2 is an element of f of E intersected with the inverse image of B. But that set is H. So f of x sub 2 is an element of f of H, but f of x sub 2 is y, or y sub 2. So y sub 2 is an element of H. I'm sorry, element of f of H. And that's what we wanted to show. So that says that B is a subset of f of H. Thus, f of H equals to B. And that ends the proof of the claim. Okay. Since A and B are separated, A closure intersect B is empty. So, the inverse image of A intersect, or A closure intersect B, which equals to the inverse image of A intersected with the inverse image of B, is empty. Since G is contained in the inverse image, this should have been A closure here, of A closure, and F inverse of B is equal to H. Okay. Then, this should have said G closure here. Wait just a second. So how are we getting this? Well, we had B is equal to F of H. So that means that the inverse image of F of H is going to be, it's going to contain H. I think this might need a little bit of thinking about here, but let's go ahead and assume that this is correct. Okay? That's correct. Then we have G closure intersect H is empty. So wait just a second on that. I'm sorry, I need to think just for a second. I think that this should say contains H. Okay, let's make that change. But that's a safer thing to say. Okay, so we have that. We can use the same argument to show G intersect H closure is empty. Okay? Thus, G and H are separated. Remember, E was equal to the union of those two guys, G and H. So right now, we're saying that G and H are separated. So E is not connected. And that's a contradiction. We're assuming E is connected. And so we came to this contradiction based on the assumption that F of E was not connected, so F of E must be connected. And that is proved. Next, we want to do something that's an important fact in calculus. State proved it. And here it is. It's a theorem. It's called the intermediate value theorem. And it's a consequence of what we just did. And here's what it says. It says, let F be continuous, be a continuous real function on the interval closed interval from A to B. If f of A is less than f of B, that's the first one, and C is a number between, or such that C falls between f of A and f of B. I'll write that down. F of A is less than, C is less than f of B. Then there exists an X element of the open interval from A to B such that f of X is equal to C. Okay. So as a proof, note that the interval A to B is connected in R. It's a connected subset of R. It's because anytime you give me two values in this set that aren't the same, then the point in between them exists in this set. That was what it took to be connected in R. We did a theorem that said that. Since f is continuous, since f is continuous, f of AB that's connected in R. Okay. Thus, by a previous theorem, f of C here's what I should say. Then that's by a previous theorem about connected sets. Based on f of A being less than C being less than f of B, that tells us that C is an element of f of the set A to B. That's the theorem that I was mentioning about here. Okay? I'm talking about being connected. Same theorem. So, there exists an X element of A to B such that f of X is equal to C. Now, since f of A is different from C and f of B is different from C, then X is an element of the open interval from A to B. And that ends the proof. Okay, next I want to talk about a definition about what it means not to be continuous, and then we'll talk about left and right-handed limits. So here's a definition. This is just it's just a word here. It says, if X is in the domain of a function f at which f is not continuous, then we say f is discontinuous at X, or f has discontinuity at X. So if you're not continuous, you're called discontinuous. Discontinuous is the word I was talking about. That's what we're defining. Okay, I want to make another definition. So here we let F be defined on A to B, that's a subset of R, and we consider any point X such that A is less than or equal to X is less than B. We write F of X plus equals to Q if F of Tn, that's going to be a sequence, converges to Q as n goes to infinity for all sequences. T sub n, that's a subset of A to B subset. Here, let's write this as X to B. Okay, X to B. Yes, we need to be X to B. Okay. Such that T sub n converges to X. And then what we'll say is F of X plus is called the right-hand limit of F at X. Well, if we've got a right-hand limit, we ought to have a left-hand limit. And we do. We're going to write that definition down analogous to the one we just had. Here's that definition. So we let F be defined on A to B, again, which is a subset of R. Consider any point X such that A is less than X is less than or equal to B. We write F of X minus equals to Q if F of Tn converges to Q as n goes to infinity. For all sequences T sub n is contained from A to X such that T sub n converges to X. That's the left-hand limit. What I want to do next is look at an example talking about these left and right-hand limits. Oh, sorry, before I leave this, in this case, again, we should write down what we call it. Then, f of x minus, which is equal to u, is called the left-handed limit of f at x. Okay, so as a quick example, if we let f of x be defined to be equal to 1 or minus 1, if x is an element, let's say from minus 2 to 0, okay, and let it be 1 if x is an element from 0 to 2. Here's what we're looking at pictorially. So minus 1 is down here. We've got open. Here's minus 2. Open there. And here, 0 we find to be 1 up to 2. All right, that's where it's defined. And then what I want to tell you is f of 0 plus, that's going to be equal to, so if you come in and write a 0, your answer is going to be 1. And the left-handed limit is going to be equal to minus 1. So if you come in from the left, the output values are around minus 1. And here's a fact. It says let f be defined on the open interval from A to B segment, and let x be an element of this open interval from A to B. Then the limit as t goes to x of f of t exists. This is the if and only if statement. I'm going to write next. That's what we had. It exists if and only if the right-handed limit equals to the left-handed limit. Okay. In this case, which equals to the limit as t goes to x of f of x. Let's do the proof. Let's let f be defined here. I'm just going to say this is parentheses, which equals in this case. Okay. So let f be defined on a to b, and let x be an element of an open interval from a to b. All right, so it's an if and only if statement, so we'll go in this direction. Suppose the limit as t goes to x of f of t exists. And let's say, let's give it a name. Say this limit as t goes to x of f of t equals to q. What we want to do is show that the right-hand limit and left-hand limit are also true. Okay? So here, let t sub n be a sequence in x to b such that t sub n converges to x. Then, okay, by the sequential criterion for function limits, f of Tn converges to Q. Okay? So, we were assuming that f of the limit is t. The limit is t goes to x of f of t exists. Okay, is equal to q. So by the sequential criterion function limits, if you give me any sequence that converges to x where none of its terms are equal to x, then f of that sequence has to converge to that limit, and that's q here. So that says that by definition, that f of x plus equals to q. All right, how are we going to show that f of the right-hand limit is equal to q? So to do that, we're going to let, let's call it S of n, do the same thing, be a sequence. I'm just using the definition right now of the left-hand limit. Be a sequence n here from a to x, such that S of n converges to x. Okay. Again, by the sequential criterion for function limits, I'll abbreviate SCFL. F of S of n converges to q, and so that means that f of x minus equals to q. So that's half the proof in some sense. Now we're going the other direction. Suppose that f of x plus exists and it's equal to q, and f of x minus n exists, and it's equal to q. Then, for each sequence, in x to b, say t sub n, with t sub n I know I'm going extra, but that's okay. With t sub n converging to x, then f of t sub n converges to q. Similarly, just using the definitions here for the left and right hand limits. For each sequence, S sub n, that's a subset of a to x with S sub n converging to x, then f of S sub n converges to q. Now, what we're going to do is we're going to let P sub n be a sequence in A to B such that P sub n converges to X. And what we want to show, there's one more thing. With P sub n being different than X for every n element of J. So look, what I'm going to try to do is show that the limit, the overall limit, the limit is it's t goes to x of f of x equals to q by showing that if you give me some sequence in its domain that converges to x but never is equal to x, that f of that sequence goes to q, and that will show that the overall limit exists by the sequential criterion for functional limits. Okay? So we'll consider the following two subcases, following two cases. Okay, so when we think about P sub n, we want to talk about how they act about x in the following sense. Case one, there are only finitely many P sub n's that are less than x. Say P sub n sub 1, P sub n sub 2, all the way up to P sub n sub I. So those are the P sub n's that are less than x. Then, if you look at this sequence, P sub n sub 1, sub I plus 1, P sub n sub I plus 2, P sub n sub I plus 3, forever, okay, which I'll denote as P sub n sub I plus k, k runs from 1 to infinity, is a subsequence of P sub n. such that P sub n sub I plus k, okay, that is contained in the interval, so we're bigger than, so it must be from x to b. And the P sub n sub I plus k must converge to x as k goes to infinity. And that's because the P sub n must converge to x. Thus, f of P sub n sub I plus k, that converges to q. Okay. Go to the right-hand limit. So this is by assumption, by hypothesis, what we're assuming. So, given epsilon greater than 0, there exists an n that's an element of J such that for all n bigger than or equal to this big N, absolute value of f of P sub n sub I plus k minus q will be less than epsilon. This should say for all k. So, for all n bigger than or equal to n sub I plus this big N, then absolute value of f of P sub n minus q, that will be less than epsilon. Thus, that tells us that f of P sub n converges to q. Case 2. There are infinitely many PNs less than X. Okay? So we'll look at a subcase. Subcase 1 is there are only finitely many P sub n's that are greater than x. And so this works, the subcase we're in, works analogously to what we just did. A few more minutes, we'll be done. Thus, or I'll say it this way then, by this similar argument, the same argument, as in case 1, okay, there exists an n sub I element of J such that for all n bigger than or equal to n sub I, P sub n is an element of A up to x, and the sequence p sub n sub I plus k. K runs from 1 to infinity, is a subsequence of p sub n. So the p sub n sub I plus k is a sequence that's going to converge to x, and by hypothesis, f of p sub n sub I plus k converges to q. So this will imply, just as it did before, that f of p sub n converges to q. So now we have subcase 2. There are infinitely many p sub n's greater than x. So they're infinitely many smaller, infinitely many greater. So we divide p sub n, the sequence, into, so we partition it into two subsequences. P sub n, we're going to say sub k, and P sub n sub L, such that P sub n sub k is going to be less than x for all k element j, and P sub n sub L is going to be greater than x for all L that are natural numbers. Since P sub n converges to x, okay, then P sub n sub k, it will converge to x, and P sub n sub L will converge to x as well. Okay, so what that says is f of p sub n sub k converges to q, and f of p sub n sub L also converges to q. And this implies, that last line I have it because of what we're assuming, this implies that f of p sub n converges to q. And that takes a little work, but not much work. So I'll just say that invers this. Thus, in all cases, f of p sub n converges to q. So, by the sequential theorem for function limits, that says that the limit as t goes to x of f of t equals to q. And that's what we wanted to show. That ends the proof. Thank you very much for your time and patience. That ends this video lecture.